In this lecture, we discuss linear approximation and introduce differentials. The idea behind the linear approximation, or any approximation, is to replace a complicated function by a simpler function near a particular point. The simplest of all functions is the linear function, and the linear approximation consists of replacing a function near some point by a line. Which line should be used for this purpose? The tangent line, of course. For example, consider the parabola y equals x squared and its tangent line y equals 2x minus 1 at the point 1, 1. Now we zoom in towards the point 1, 1. We see that the parabola lies very close to its tangent line. We zoom in more, and the curve becomes almost indistinguishable from the line. By zooming in toward a point on a graph, we see that the graph looks more and more like its tangent line. Here is the reason why. By definition, the derivative of a function f at a point a, f prime of a, is the limit as x approaches a of f of x minus f of a divided by x minus a. This means that when x is close to a, f prime of a is close to the expression under the limit, f of x minus f of a over x minus a. Let's multiply both sides of this equation by x minus a. We obtain that f prime of a times x minus a is nearly equal to f of x minus f of a. Now we add f of a to both sides and get f of a plus f prime of a times x minus a is approximately f of x. Notice that the expression on the left-hand side is exactly the equation of the tangent line to the curve y equals f of x at the point a f of a. Therefore, when x is close to a, the values f of x are close to the corresponding values on the tangent line. The approximation f of x is approximately equal to f of a plus f prime of a times x minus a is called the linear approximation or tangent line approximation of f at a. The linear function whose graph is the tangent line at a, that is L of x equals f of a plus f prime of a times x minus a, is called the linearization of f at a. Let's look at an example. Find the linearization of the function f of x equals square root of x minus 1 at a equals 10 and use it to approximate square root of 8.97. The linearization of f at a equals 10 is given by the formula L of x equals f of 10 plus f prime of 10 times x minus 10. We need to compute f of 10 and f prime of 10. To compute f of 10, we substitute 10 for x into square root of x minus 1. We get square root of 10 minus 1 equals square root of 9 equals 3. To find the derivative of f at 10, we first compute f prime of x, that is square root of x minus 1 prime. Since square root of x minus 1 is a composite function, we use the chain rule. The derivative of the square root is 1 over 2 square root of x minus 1 times the derivative of the inside function, which is 1 in this case. To get f prime of 10, we plug in 10 for x in the derivative. 1 over 2 times square root of 10 minus 1 is 1 over 2 times square root of 9, which is 1/6. We substitute the values into the equation for L of x and obtain the linearization L of x equals 3 plus 1/6 times x minus 10 equals 1/6 x plus 4/3. Let's use this formula to approximate square root of 8.97. We set the expression under the square root x minus 1 equal to 8.97 and get x equals 9.97. Therefore, square root of 8.97 equals the value of f at 9.97. We know that when x is close to 10, the value f of x is close to the value of the linearization L of x. Since 9.97 is close to 10, f of 9.97 is approximately L of 9.97, which equals 3 plus 1/6 times 9.97 minus 10. Notice here that I am using an unsimplified expression for L of x to plug in the value 9.97. It is easier to carry out the computations in this way. 9.97 minus 10 is negative 0.03. We divide it by 6 and get negative 0.005. After adding 3, we obtain the answer 2.995. Let's look at another example. Use a linear approximation to estimate cubic root of 8.6. The difference between this example and the previous one is that we are not given a function or a point for linearization. The obvious choice for a function f of x is cubic root of x. To pick a point of approximation a, we need to make sure the following two conditions hold. First, point A has to be reasonably close to the value of x we want to approximate, in this case 8.6. Second, we should be able to compute the exact value of f of a. The closest integer to 8.6 is 9. However, we are not able to compute cubic root of 9 without a calculator. Another integer which is close to 8.6 is 8. Since we know that cubic root of 8 is 2, we pick a equals 8. Then cubic root of 8.6 is approximately the value of the linearization of f at 8 for x equals 8.6, which is f of 8 plus f prime of 8 times 8.6 minus 8. To find the linearization, we need to compute f of 8 and f prime of 8. F of 8 equals cubic root of 8 equals 2. To evaluate f prime of 8, we first find the derivative of f of x. Since cubic root of x is x to the 1/3, the derivative of cubic root of x is 1/3 x to the negative 2/3. Therefore, f prime of 8 is 1/3 8 to the negative 2/3. We write 8 to the negative 2/3 as 1 over cubic root of 8 squared. Since cubic root of 8 is 2, 2 squared is 4, and 3 times 4 is 12, we get 1/12. We substitute the values into the approximation and get cubic root of 8.6 is approximately f of 8 plus f prime of 8 times 8.6 minus 8 equals 2 plus 1/12 times 0.6 equals 2 plus 0.05 equals 2.05. The ideas of linear approximation can be expressed in terms of differentials. Differentials play an important role in more advanced mathematics, but we shall treat them merely as symbols denoting a change in the value of a function. If x is an independent variable, then the differential dx represents the change in the value of x, usually very small. Since x can take on any value, dx can also take on any value. That is, we can treat dx as an independent variable. If y equals f of x, then the differential dy is defined in terms of dx by the equation dy equals f prime of x dx. So dy depends on the values of x and dx. For example, let's find the differential dy of each function. In part A, y equals sine squared x. By definition, differential of y dy equals sine squared of x prime dx. We use the chain rule to take the derivative of sine squared x. Since the outside function is the square and the inside is sine x, we get 2 sine x cosine x times dx. In part B, y equals tangent of 2 plus 5t. So y is a function of t. The differential of y dy equals tangent of 2 plus 5t prime times dt. We use the chain rule to take the derivative of tangent of 2 plus 5t. Since the derivative of tangent is secant squared and the derivative of 2 plus 5t is 5, we get 5 secant squared of 2 plus 5t times dt. In part C, y equals u square root of u plus 1. So y is a function of u. The differential of y dy equals u square root of u plus 1 prime du. We use the product rule to take the derivative of u square root u plus 1. We get square root of u plus 1 plus u divided by 2 square root of u plus 1 times du. Now let's reformulate the linear approximation in terms of differentials. We use the tangent line at point with coordinates a, f of a to approximate the curve y equals f of x for x near a. We are interested in determining the effect of a small change in x. As before, we denote the change in x by delta x, that is, delta x equals x minus a. The corresponding change in y is denoted by delta y, that is, delta y equals f of x minus f of a. Delta y is the vertical change from a to x in the graph of f. The linear approximation of f at a is given by the equation f of x is approximately equal to f of a plus f prime of a, x minus a. We subtract f of a from both sides and get f of x minus f of a is approximately f prime of a times x minus a. Recall that f of x minus f of a is delta y and x minus a is delta x. Thus, in the new notation, we have delta y is approximately f prime of a delta x. When dx is delta x, delta y is approximately f prime of a dx, which is the differential of y dy. The vertical change in the tangent line is slope times the horizontal change. Since the slope is f prime of a and the horizontal change is dx, the vertical change in tangent line is f prime of a dx, which is exactly dy. Therefore, on the graph, dy represents the amount that the tangent line rises or falls, whereas delta y represents the amount that the curve y equals f of x rises or falls. What the linear approximation does is use the vertical change in the tangent line as an approximation to the vertical change in the graph of f of x. When delta x is small, the two quantities, delta y and dy, are nearly equal. Our final example illustrates the use of differentials. Use differentials to estimate the amount of paint needed to apply a coat of paint 0.05 centimeters thick to a hemispherical dome with diameter 50 meters. We start by drawing a diagram showing a cross-section of a hemispherical dome 50 meters diameter with a coat of red paint 0.05 centimeters thick. We denote by y the volume of a hemisphere of radius x. Since the volume of a sphere is 4/3 pi times radius cubed, the volume of a hemisphere is half of that. So y equals 2/3 pi x cubed. To calculate the amount of paint, we need to find the difference in the volume of two hemispheres. The inner one with a diameter 50 meters and the outer one where we added the thickness of the paint. The change in radius of the spheres delta x is exactly the thickness of the paint, 0.05 centimeters. Since the diameter of the dome is given in meters, we express delta x also in meters. 0.05 centimeters is 0.0005 meters, because 1 meter equals 100 centimeters. The diameter of the dome is 50 meters, thus the radius is 25 meters. Since y of x is the volume of the hemisphere with radius x, the amount of paint is the difference y of 25.0005 minus y of 25, which is delta y. Linear approximation tells us that delta y is approximately dy at 0.25. This equals y prime of 25 dx. Here dx is the change in x, 0.0005 meters. So we get y prime of 25 times 0.0005. To complete the problem, it is left to compute y prime of 25. The derivative y prime equals 2/3 pi times the derivative of x cubed, 3x squared. This gives y prime of 25 equals 2 pi times 25 squared equals 1250 pi. Therefore, the amount of paint delta y is approximately 1250 pi times 0.0005, which is 0.625 pi cubic meters. We finish with the summary of the lecture. The linear approximation is the estimate f of x is approximately equal to f of a plus f prime of a times x minus a when x is close to a. The function L of x equals f of a plus f prime of a times x minus a is called the linearization of f at a. If y equals f of x, the differential of y is dy equals f prime of x dx. In terms of differentials, the linear approximation is the statement delta y is approximately dy, where delta y is the change in f of x for a given change dx in x. This is the end of our lecture.